used Utah's scientific computing institute, which is called SKI. And it's actually very well known. It definitely predates MICDE by quite a bit. Anyway, Pania's work is broadly in computational mechanics and materials. She has an interest in developing multi-scale methods, extracting information from lower scales, and obviously very advanced models and simulations of materials and mechanics. The work that she's going to talk about today pretty much combines all of that. And so it's my pleasure.
Thank you so much. Thank you so much, Krishna. Thank you all for coming this Friday afternoon. Can you all hear me okay? Yes, so I'm wearing mask to protect you because I was in the airport, so I just don't want to make anybody sick in case I get anything. Yeah, thank you all for coming. Today I'll be basically talking about mechanics of hierarchical porous structures, and I know that this is a computational seminar series, but I'm going to take a kind of a non-traditional approach and talking about also the experimental and the design aspect, and then towards the end how they are all coming and helping with the numerical aspect of these hierarchical porous structures. So my goal is hopefully by the end of the day I can convince you that these porous materials are important, and hopefully we can achieve that. Quickly, as Krishna mentioned, my background is computational mechanics, but when I did my postdoc at India labs, I recognized that it's very important that we all work together. We can't just sit in the corner and write programs and hope that everything is going to work. So I started working a lot with experimentalists, and I learned a ton from them, and I realized that how lucky I was that I was not in the experimental mechanics, because it takes longer and longer than simulations to get one experiment done. But so now my motivation is to look at multi-physics processes and looking at looking at experiments, and also obviously developing theoretical framework for multi-physics systems and coupling them with the simulations and obviously data sciences. And that's mainly through my joint appointments with the School of Computing and working with my brilliant computer scientist friends. But the name of my lab is Integrated Multi-Physics Lab, basically integrating across these 4 trust areas. And multi-physics is because yeah, mechanics is very exciting, but when you look at the world, everything is kind of coupled. All these physics, they are coupled, and I like the excitement of challenging, of dealing with the skills, and also both temporal and spatial skills. And also, I would like to acknowledge that most of this work that I'm presenting today, it's this brilliant students, postdocs, undergraduates that they joined my lab, and they made this work it was possible to be presented, as well as the funding agencies that they've been funding us through my time at University of Utah. So what is porous media, and what is basically heterogeneous porous media? I don't know how many of you like washing dishes by hands. Anybody? Not even one single person? That's, oh, good. So sponge is an awesome, good example of porous media. And I love a sponge because when you pour soap and you add water to it, you are dealing with two-phase flow, right? Moving through these porous systems. And also I'm OCD, so I always like washing dishes by hand. But when you look at your skin and you look at your teeth, your bones, so they're soft and hard tissues. Many of them, they are made of porous systems at different levels. And also looking at the leaves, I am fascinated by how, when you look at this under this, you don't even need to look at the high resolution microscope. When you look at the leaves, you see these porous networks that they are creating, these networks that passing the nutrition throughout the leaves. And now people, they look at the nature and they said, well, nature is taking advantage of these porous systems. Why not we create porous systems, artificial porous systems, to give us benefits? And foams is one example. The old ancient brick and concrete buildings, they are all made of porous systems. And well, my work is mainly looking at the geological systems, and you will see today. Geological system, the motivation of that started with Sandia because under the Department of Energy, they wanted to extract or store energy in geological system. And also, I'm a chocolate lover. So who wants to have a bite of the hard, soft brownies, right? So we all want to benefit from this porous system. But what's very challenging is the resolutions of these porous scales. So sometimes they are at the single nanodigit or even 1/10 of the nanoscale, and it goes all the way to 100 microns. It's very, very, very difficult when you have these hierarchical porous systems and you try to characterize the system. And sometimes we have only micropores, sometimes we have mesopores and macropores, and life is easy when you have one class of the pores. But also the other benefits of the porous system is that, well, as you can tell, high surface areas, right? So it creates this porous system, it makes the low density of the materials, and that's why we are looking at the biological, at the geological systems or bio-inspired system, trying to mimic the porosity or the porous media and create these foamous structures. And as a result, we have low resistivity, low conductivity, and there are many other benefits to this porous system too. But it's not all good, and it's not, life is not amazing by just moving to using porous media. There are so many challenges, and as I mentioned, the scale characterizations of these pores across the scales has been challenging. Designing materials, so we always want to, we are a bunch of engineers, we want to design things at the larger scale. We want to design buildings, and we want to make cars and bridges and larger and larger materials. We might be able to control these pores at the nanoscale or the smaller scale, but we cannot expand them to this day. We cannot extend them to the larger scales. And improving this, the porosity of these systems is another challenge. It comes from the chemistry because the templating. So we know how to create the pores. For example, we know how to 3D print concrete, but we don't know where to put the pores. It just happens, right? So this kind of, it makes it's one of the biggest challenges in material sciences to this day. After all material scientists, including engineers, we want to have materials that they are stronger, and most of the time we want them lighter and tougher, right? So if you talk to NASA folks, they are always working about creating new materials and any other material scientists, I guess. So porous media and tailoring properties based on their structure has been one of the challenging areas of material sciences. And I don't know why it's jumping up and down. So this has been noticed by many funding agencies, including the Department of Energy. So for various reasons, we all need drinking waters. So we need to extract this water from the drinking water resources that we have, that most of the time they are under the ground. And by the way, subsurface is the largest porous media on the planet. And we need to be able to clean up this and filter it through and get drinking water. Another thing is energy harvesting. Different type of energy harvesting, they are relying on the porous system and biological engineering. I have oil and gas there. In the older generations, oil and gas, it was heavily based on the movement of the gas and porous, in the porous system. These days, oil and gas is moving away. It's not going to go away, I guess, forever, but it's being replaced by geothermal system, which also relies on the porous media. So coming from the Department of Energy, these are the reports that I've been following up. If you look at these results, these reports, these are most scientific reports written by the basic energy sciences. They are talking about the importance of the porous media, energy and water, and chemical upcycling of the polymers, all of these. If you read and you just simply Google for the porous media, you will see how important they are. And how much they are talking about the importance of the porous media in our life. And it doesn't end with with the National Academy of Sciences and Engineering, that the decades of studies on material sciences, as you can see on this on the cover page, they are highlighting the importance of the porous system. And recently, about a couple of months ago, the National Academy of Sciences and Engineering and Medicine, they put this report out, Physics of Life. This is the area that many people these days, they are fascinated by, to try to understand the origin of the life and how we can mimic it in our material designs and so on. But when you look at the cover, when I saw it, if you flip that cover, that's the main cover. If you flip it, it actually during that time we recently published this work with one of my colleagues, Stephen Nelway, that he's a bio-inspired person. He's a material scientist. He looked at the nature, and one day he came to us and he said, well, we are doing this experimental work on rhizomorph. I didn't even know how to pronounce rhizomorph and what rhizomorph is. It happens to be a fungi. And they wanted us to do this modeling of their porous network. That's the image that they gave us. And if you can see, it kind of close to what that image is on the report from the national academies. And the density variations in the porous structure, that's very common. When you look at your skin, there are different layers. When you look at your brain, they all have these different densities of the porosities. So hopefully by now you are convinced that porous media are kind of important to study. And I doubt that it's going to go away because it's part of our life and we are relying on it. This image, it's taken from a center that is built based on the porous media. The center that I'm part of it is funded by the Department of Energy, and my role is to understand geo-inspired materials, understanding the mechanics of them. What do I mean by the geo-inspired materials? They want to be able to create artificial geological systems that they respond to the way that they want it to respond. So for that reason, they are starting with, for example, that's a piece of rock that you get it, you do the mapping, you do all the chemical analysis, you do high resolution imaging, and I'll come back to all of this and talk about the importance of the computational mechanics and sciences in these processes. So we go through all of this, we can create this digital rock, and you all have heard about digital twins, right? It's a kind of similar concept. You look at the digital rock, and then you want to be able to use this one as your resource to do whatever that you want, experimentally or computationally do a lot of work on this digital rock. But what do I mean by experimentally? Basically designing things that they give that properties, because we cannot drill all the way going 2 kilometers below the surface ground and get piece of rock, right? So, so my goal is to, as part of this talk, is to talk about the importance of these processes, design, manufacturing experience, and simulations, and how they go hand in hand. And hopefully by the end of the talk, if I can answer these two science questions. What's the role of pore morphology and macroscopic mechanical and fracture properties? And to what extent do smaller pores, and by smaller pores, those micro nano pores, they contribute to the overall behavior? And if we can answer those, we might be able to connect some part of this loop. So the first part is basically looking at the micro nano porous structures and designing them. We know that these systems, they are complex. So you can see there are these hierarchical porous structure, and it's very heterogeneous. We thought, well, if I want to understand the behavior of the pores, I need to look at a single pore. I don't know why these things, they are jumping up and down. So we started looking at the nanoscribe. Nanoscribe is you can print the structures at the nanoscale. And nanoscale, I don't mean that single digit nano, is 150 nanometer. That's the range of the feature size that you can design. And then you can go through the process of fabricating this. You can have 3D nanostructures, and you can mechanically test them. Thanks to Brother, they are coming up with these new devices that you can do compression tests under the SEM or even TEM and understand the deformations of these structures under mechanical loading that you are applying. So this is an example of the Brother. This is the probe, and you place your samples here. You can compress them. You can also apply tension, you can apply torsion, and also you can apply fractures and fatigue testing to them. So these are very difficult, challenging tests, very, very complex. So these are the samples that we printed. We wanted to understand the role of the size effect at the nanoscale. They look like a cube, but they have pores in them. So internally, there are different pore structures, and the probe comes and they apply mechanical loading, and we want to understand that how we can decouple structural behavior from the materials response. So these are the setup that we have. So obviously, we needed to understand the mechanics of the solid structure and the different pore structures. As you can see, the porosity is changing. And we created this template and had multiple of each samples for the reproducibility and then doing the testing. But what's important, I want to highlight this nanomechanical response, that the pink region is all the solid structures. The solid structures with different aspect ratios to capture the size effect. It goes to the blue region. Blue region has the lower porosity. So we introduce some sort of porosity, but different type of the pore shapes. And the green region is more porosity. So they're increasing the porosity. So as you can see, there is a shift in the behavior. And if you follow the linear elastic region, just focusing on only the elastic properties, we see there is a degradation, which is obviously a function of the porosity. This is a known factor in the macroscopic level, but at the nanoscale, this is, to my knowledge, this is the first time that the porous structure is being tested at the nanoscale or higher, a couple of, 100 meter long nanoscales. And then, it's the behavior of the softening and the unloading. Those are other stories that also they reveal the pore dependency. So these figures, basically, the first one, it's a zoom in, so you can see that how the modulus is changing. And this one, it highlights the role of the pore morphology. So we have the same porosity in both cases, but obviously the shape of one of them is a circular pore through this tube, and the other one is the oval shaped pore. And there is a change in the Young's modulus. And as I said, we looked at the anisotropy in the systems, in the softening part, the response, and then the plastic response, all of those it's not the focus of this talk. I just wanted to highlight that at the nanoscale, these pores, they influence the overall mechanical response of the structured materials. But and these are some, they were supposed to be videos showing that how when you are compressing this shape, how they are deforming. Throughout this, you see there are arrays of the pores and you see the bulging shapes, right? This one, it shows that that's a solid one, it just bulges out, but this one has the pore somewhere here in the middle, and you can see the impact of the pores. The oval shape, it shows different responses. And what do we do with this? We have these single pores. What's the point of this, and what's the connections with the design and computational processes? How we can move on and learn from this and design structures that they give us properties that we want. After all, I want to be able to understand complex porous system and porous morphology. So with that, we needed to go to Brookhaven National Lab. And this is where I guess in my opinion, magic happened. We had these samples that after working months and months and months of preparing the samples to become 200 microns tall and 10 micron diameter, we had to design a fixture that we can load this while we are scanning this. And while we went to Brookhaven National Lab, because they have the fastest scan in the world. At every time you are loading your sample, you can scan your sample. And this is where the role of the computational mechanics and people that are doing material science plays a significant role. Because each of those tests that we are doing, we are creating these high resolutions, porous structures that they keep evolving. So again, these were supposed to be videos. This is the stress strain curve. Each of these are thousands of the frames that they show how these porous structures is moving. And the goal is we cannot do this testing. Each of these tests, we had only 3 days, and each of these tests, they take a couple of hours to set them up. And what's the benefit of getting this knowledge? The benefit is that if we know the correlations between the porous structures and mechanical response at that scale, we can go back and design materials, or we can set up computational tools and apply different type of loading. Instead of compression, we can shear them, right? So this novel experiment, it took us 6 months working with the School of Computing, that they are experts in computational visualization, dealing with large data, to automate the whole process. Now, what we are working on is that while somebody is running this experiment, we want to be able to hold on the experiment at this time if the crack is initiating and change the loading, maybe start unloading or applying shear loading or something else. So on-the-fly analysis of running these large simulation data sets. And this is what the Department of Energy has a lot of interest in, integrating experiment and simulation and design at the same time. And all of this is, as I said, it took us a couple of months working with the experts and using their simulation tools to even be able to construct this. We used a lot of machine learning tools in creating these constructed images, reconstructed images, and still we are not there. So, and this is another experiment that it's a fracture mechanics testing that, again, at the larger scale, at the smaller scale, they call it double torsion test. It's similar to 3-point bend testing, but you want to be able to see how the crack is propagating. And by high resolution images of this, when you have these porous structures around, you want to be able to understand that how the path of the crack and the energy of the crack is dominated by the underlying porous structure. So these are the part of the experiments, how we can benefit from the experimental mechanics to help us to understand design better. So now going to the nano micro, I'm going to now focus on some computational aspect of the work that we've been doing. But I hope that I'm sorry, I don't know why this slides they keep shifting in down. So for this, again, the focus is at the nanoscale. We start from nanoscale going back up to the continuous scale. Our focus is on silica-based materials. And if you look at the nature, I'm too short to not point out that those, and the laser is not working. So if you look at those, the porous structure, that's the middle image is a good example of the hierarchical porous structure. Each of those big balls that you see, if you look through them, you will see a lot of porous spheres underneath. And also you see that when they are meeting together, there is this triangular pore shapes being created. So there is a higher porous mesoscale pore that has a triangle shape. Here, the other example is it shows the circular pore. And if you look at those, they are like a sugar cubes on top of each other, or a bunch of piece of cubes on top of each other. You can see there are regions that there are these triangular or cube pores. So by looking at the materials being synthesized by the material scientists, we know that there are these porous structures. So the goal is that to understand them at the atomistic level. So we set up the simulation model. You may ask, how we end up at this size, 29.41 nanometer. So that goes to a lot of setting up simulations that making sure when you are applying periodic boundary conditions and you are extracting the properties, you converge to the solutions that you want. It gives you always the same properties that you wish, and it's independent from the domain size. So we increased the size, and we did that study. We realized that this is the size, the minimum, smallest size that we can do, and it has 86,000 atoms in that scale. If you go lower than that, your properties that you are getting, it's domain dependent. So these are tension tests, simple tension tests, because we are interested in the mode 1 fracture too. So that's another obvious justification for the mode of loading. So we look at different pore morphologies. So what we want, the mimicking the porosity at the scale that experiment is telling us. So that's driven by the experiments. And we do the back calculations to figure out what dimensions and what size pore we need to use. So that's how we came up with this different cases, 9 total with the 1 solid case. For this, if you are familiar with numerical simulations at the atomistic level, we are using lamps. Well, I need to be loyal to Sandia Lab, so and also lamps is free. They were offering us a lot of service when we had questions. And also one of my colleagues, he is a developer of the REACT effect. So as part of this center, we wanted to bring all of these resources together. We know that we want to capture the chemistry, and also we want to capture the mechanics. There are issues with lamps because when we are modeling silica, or any materials, it needs to go through this rapid heating and cooling process followed by relaxations. So the question is that when you start with crystalline materials and then you create these amorphous structures, do you get the same structure, the same properties, or you are messing up with the whole response of the material? And that's why we have the radial distribution functions that it confirms that, well, this amorphous structure, we just change the orientation, it has the same property. So these are unit cells. So now we stack them on top of each other. We create the structures that it goes back to the size of that of these structures. So each of these, they are a stack of unit cells. And now we need to create a porous structure. So we need to remove atoms from the center to give us this locations. Also removing atoms, it's not that easy. It's not just you remove them. You need to make sure that there are not any dangling bonds in there. So, and we wanted to make sure that we are roughly about 86,400 atoms for all cases. They are rough estimations. So then after that, we look at the simple response, mechanical response of these systems. The figures on the top, they show cases without pore, with pore in different porosities. So the black curve on all of those, it's the reference case when there is no pore in the system. Obviously, it has the highest strength. But when we are increasing the porosity, if you just trace one case, the blue, and come down all the way to the left, to the right, you would see there is a drop in not only the slope but also the strength. First, we thought that the cylindrical pore should give us the highest strength. The question is, well, what's happening? Why the square-shaped pores has the highest strength? And when we look at the system, we I did not mention that we set up all of these. These are the unit cell, and as we all know, when we set up unit cells, there are periodic boundary conditions that we apply to them for the, I guess, the easy convergence. So all of these are periodic. So there is another pore here, which is the distance from this pore to this pore, or the edges, or there is pore on the left, right, and front and back. The next spacing between them, we call them ligament length. So that ligament length is the dominant factors deciding that how, which one is the strongest case. That is the gap that you have a solid materials, basically. And that was the explanations of the peak stress values. And this is the stress values at the global level for the entire system. But what about the Young's modulus? The response of these materials in the macroscopic level, we know that there is exponential decay by introducing the porosity into the system. However, if we plot the Young's modulus from each of those cases, we don't see those exponential decay. The reason for that is that because at the nanoscale, the porosity change is 2, 3, 4%. The macroscopic level, 30, 40, 50%, and for foam, it goes even higher. There are porous foams with 90% porosity. So this is the small changes, but the decay is what we expected from the macroscopic level. But what is interesting, if you replot the Young's modulus now in terms of the potential energy per number of the atoms, you see very distinct grouping. That's a function of the pore morphology. So the pore shapes plays an important role in the nanomechanical response of these materials. And this is again, it's the distributions of the potential energy that clearly shows that which case has a higher potential energy. How about the critical energy release rate? Why do we care about this? At the end of the day, we want to make sure that we are preventing things from failure, and we want to control fracture. So we look at the GIC value, the critical energy release rate. We plot this for all those 9 cases, all based on their porosity being combined. We see that this is unlike what happens in the macroscopic level. There is a drop, but there is not much variations in the GIC value when you are changing the porosity, which is very, very different than what you see at the macroscopic level. So it means that the change in the porosity as a first order parameter does not dominate the GIC at the nanoscale. So it doesn't have much of a control, I guess, on the GIC. But when you look at the GIC in terms of the ligament length, we see clear distinctions in terms of the pore morphology. So that ligament length that I explained, the net area, the gap between the pores in the neighboring region, that's what has a clear dependency on the GIC value. So basically, I guess the takeaway message is that by changing the pore morphology, you can change the ligament length, and yeah, you will make some changes in the GIC. But the porosity, the first order parameter, does not have any control whatsoever on the GIC value or controlling the fracture at the nanoscale. So what is the role of the defect in these systems? If we have a defect in the system, that the tiny crack that I introduced in the system, we want to know that if we have different pore morphologies, circular, square, and triangular, and we have this different crack orientations, how it impacts the overall response of the system. Do we need to account for those small features in the system? Does it matter or not? And again, we are looking at the amorphous system, amorphous silica system. So we look at these different cases. Again, the same periodic boundary condition. We kept the temperature and the boundary conditions everything constant for all of these cases. These are the response. As you can pay attention on this circular and square and triangular case, you will see that the black case, which is responding to the zero order, the defect when it's in the zero angle with respect to the pore. In the circular and square case, they follow 0, 45, 90. So by increasing the defect order, the change in the stress strain response corresponds to that orientation, but not so much in the triangular case. And the reason for that is because circular and square case, they have the symmetry. In the triangular case, you are breaking the symmetry of the system. So therefore, we don't see that. And again, when you go back and look at the ligament length and all of those, you see that the explanation would be more clear. So overall, the Young's modulus for the circular and square case, which have the symmetry, by increasing the angle of the orientation angle of the crack or the pre-existing crack, there is a drop in the Young's modulus. For the triangular case, the smaller case corresponds to 60-degree angle. And we were wondering what happens to the energy release rate. Does that tiny crack, it has an impact on fracture propagations? We saw that in the other cases, the GIC was not impacted by the porosity, but what about this small crack? If you look at these cases, the circular and square case, we see similar trend. By increasing the orientation, there is a drop in the GIC value, and there is the same thing. At the 45 degree, there is a peak, and then it drops down. So it doesn't follow that it's because of the structural anisotropy that the triangular portion introduces into the domain. But if you look at the bonds that they are breaking within those regions, that would explain why the 45-degree angle has the highest amount of the GIC value for the triangle. Basically, more bonds are breaking in the domain between the crack and between the pore. And this is going back to the ligament length, showing that the gap is introduced by different orientation. It defines the crack pattern at the macroscopic, at the nanoscale. So in the macroscopic level, if you run the simulations, most of the time the crack curves towards those defects, but not so much in the micro level. So this is just trying to bring the experiment at the nanoscale and the numerics at the nanoscale, and trying to understand what happens with these basic fundamental properties, because we need these properties to be able to run things at the macroscopic level. So now I would like to shift to one scale up, from micro to macro level. For that purpose, we look at the homogenization tools. We use, there are various methods for homogenizations. Most of them, it's basically you are looking at two different boundary value problems and you solve them and you try to understand the macroscopic response or the response at the larger scale. For this work, we decided to go with HMM method. There are reasons that we picked this method. There are some of them are listed here. I'm not going to take your time this Friday afternoon to walk you through this. But in our by this publication, we explain why we were interested in finite element method, that it's based on a heterogeneous multi-scale method. But what this method does, similar to any again homogenization problem, you look at different scales, you take the average and you pass this information. There are different methods, like the most common one, I guess, is the FE squared, that people, they solve two different problems, they pass the information back and forth. But for fraction problems, these become really, really challenging, because the fraction is this dynamic problem that's happening at the macroscopic scale, and you want to keep looking and going back. The concept of your RVE is broken, right? So we needed to use this homogenization, but the homogenization is only to give us the material, the constitutive parameters. That's the only reason that we are doing it. And we get the constitutive parameters, so we don't need to know them at the macroscopic level. We have a bunch of SEM images, microstructural images, and we can run these homogenization to extract the properties. And at the macroscopic level, to capture the fracture evolution, we just use simply phase field. And so for the phase field, we didn't have any experimental data for the phase field fracture. We did not have any experimental data, but we relied on MICDE's work as well, because we wanted to introduce the water into those pore systems. So MICDE is one of the pioneers that he introduced fluid flow or we introduced phase field fracture in porous media. So we looked at his data. So as you can see, it's coming from MICDE's example problem, this classical problem, single edge problem. But we wanted to make sure that when we are looking at these two-scale problem, looking at the homogenization problem versus looking at it only at the microscopic level, we get the same results, and that's what this plot is showing. So this is duplicating MICDE's problem, but looking at it at the macroscopic level. That's what he did, and then us looking at the two scales, and we can see that the low displacement curve of this system is reproducible. So now we want to understand the role of the pore morphology, but now we are not at the macroscopic, at the micro level. We have different porous systems. There are these two pores, micropore 1, micro 2, and micro 3. They have the same porosity, but the pore shapes are different. And at micropore, obviously, it's we are introducing additional porosities by additional pores to increase the porosity. We picked that complex problem because we wanted to have these pores to look at the fracture path as a result of these pores for a complex loading geometry, not just simple single edge problem. Case 1 up there responds to the micropores. As you can see, the fracture path is very smooth. There is no pore, there is nothing, so we have multi-level, but it's a multi-scale, but no underlying pore. This case and this case, this one is a case when we have a same porosity for both of these. This one, the fracture path stays smooth because we are using circular pore. But if you look at this, there are this zigzag fracture pattern, and that's the result of the underlying microstructure pores having these sharp edges. Also, the change of the aperture. So we are tracing the maximum apertures at different, corresponding to the same coordinate system. You can see there is a drop also in the change of the opening of the fracture. And these are very important when we want to calculate the permeabilities and looking at the fluid flow within the system. And this one obviously is when we are increasing the number of the porosity. So the smoothness is back. We are using those circular pores, and also the aperture size is increasing. So through this problem, we are showing that they are highlighting the importance of the underlying form structure and the fracture path at the macro scale.
So in that case, how is the porosity included in the phase field?
So the porosity is not included in the phase field. So remember that when we do the homogenization, so the porosity comes through the homogenizations and then the property. The phase field is right at the continuous scale, but it sees the impact of the porosity. So those they are just basically coming through the homogenization.
Oh, I see. So you have the homogenized energies in the
yes.
And the effect of homogenizing across different types of porosity is reflected in this matrix.
Yeah. So then we started asking ourselves, well, so these questions of the higher order parameters, what's the role of this? We know that you can have these homogenization methods, and you can look at systems with complex microstructures. It can do different, as I said, different type of homogenization approaches. But theoretically, we need to have a sense of what's the role of these pores, because remember, we want to tie everything. We want to do design, experiments, simulations, and manufacturing, all of this being part of one happy family. And we need to be able to understand this, the role of these higher order parameters. But what do I mean by higher order parameters? Means shape, size, and pore distributions. So we looked at a different homogenization approach, basically saying that that's the basic, I guess, energy that we set up for the RDEs at the micro scale and macro scale, different conventions that everybody is using. But at the micro scale, we use only first order parameters. We don't account for the interactions of the higher order parameters at the micro scale, but at the macro scale, we try to account for those. And this is where they introduce this complex tensors, higher order tensors, that we thought that we are helping ourselves, that we can figure out these tensors and then we can design them. But looking at the higher order tensors, it created complexity in our design systems, that we are still trying to understand what's the real physical meaning of this and how we can control these tensors at the macroscopic level. But this formulations is basically we set up our simulations looking at the first part is just the mechanics, and recently we finished the thermomechanics using at the same thing, and well, we have another set of this for the temperature field too.
Pania, if I may just ask you about the higher order tensors, I'm presuming you're using strain gradients there, right?
Yeah.
Has there been any consideration at the macroscopic scale to the energy being respecting the symmetries and other types of things, or would that just come under restrictions of the types of the tensors that you're considering?
So we wanted to make sure that so we are not breaking any thermodynamics laws and everything is conserved. So those created a lot of constraint, and but we consider them if that's the question that you are asking. But what we found it challenging is that I just talked about it when we introduced that triangular pore. We could not, if you allow me, I guess I'll tell you where the issue is. So for the circular pores, we implemented this simulations in Phoenix. We went through, this is basically the flow work of the setup, and periodic boundary condition and all of those good things that all of you know. So we said, well, let's look at different pores. At the different pores that they were inspired by the nanoscale that, as I said, it exists in the nature. We have those circular, square, oval shape, and triangular. When you look at the homogenized modulus of these values, almost for the change of the porosity, and we changed this porosity based on the percentage of the porosity based on what's common at the meso scale. You don't see much of a difference in terms of the circular and square cases. So it's independent of the porosity is the dominant factor based on first order parameters. When you create ellipse and triangular, these two obviously are the symmetric cases. With the triangular, first of all, you can see we couldn't increase the number of the porosity because of the size of the pores, like reaching out the boundaries. With the eclipse and the triangular, we see distinct behavior of the pore, underlying pores. These two, they created an isotropic, and then material scientists, they call them, I don't know, the metamaterial people, they call them, there is a special name for the triangular. In this case, it gives us, we could not preserve for the triangular. And when we introduce, we've been looking at it, we've been talking with many people, and apparently this is an active area of the physics people. They are looking at it to see what's happening with the triangular. Well, we know that the symmetry is broken, but what's happening that we cannot have those constraints anymore. Oh, I guess I did not put the other figure because I have a figure that I guess I forgot to upload the right one. So when we plotted this work is published, you can look at it. It's the higher order, the C tensor and G tensor. The triangular is the one that gave us a lot of problem. But with the circular and square shape, we could move on. But again, our main problem is that we don't know what's the physical meaning of this. I don't know if anybody here, if they can help. The goal is to be able to understand the physical meaning of this higher order tensors, to be able to control them. But when we don't know what they physically mean, we cannot do the structures.
So did you think about like making connections to HLB solutions?
Yeah, we looked at actually, we were within the upper bound, lower bounds. We looked at all the theoretical existing things. Yeah, so there was no, is that what you are asking? Meaning we are within that range?
Yeah, so I was even wondering like if you could use HLB solutions and it's also try to compare for the different shapes, like how close you are to the HLB solutions in terms of if you can extract out like the stresses.
We did look at the concrete examples because they have the higher porosity, the porosity is being characterized, they have the properties, and we show that when we are looking at different pore shapes, we are following the plot, right? But they have all these exponential functions, the parameters that you can fit it and basically adjust it. So that wasn't an issue. We were within the range at the micro level. However, at the nano level, none of those they follow the trend. So we were much lower, and that makes sense. You know, not everything translates at the nano scale, but for finding the relationship, you mean the physical meaning of these tensors?
Yeah, I was wondering like if one could use the HLB solutions to really kind of do the micro scale, the macro scale mapping. I mean, if in the homogenization that you were doing, because you want to construct an energy density at the macro scale where you don't want to think about the pores anymore,
yes.
Right?
Yeah.
So could HLB solutions give you a way of it?
Well, so we don't at the continuum scale, we don't want to be worried about the pores, but when we are designing them, we need to go the bottom up approach, right? So we need to be able to care about those pores, where to put them, and that's why we thought that these approaches can help us to know where and what size and what distribution. But when you go with all those classical approach, they give you the response at the macroscopic level that we are within that response.
But what I was thinking was that like an HLB solution, you take the HLB solution and then you homogenize.
Oh, no, we did not look at that. Sure, yeah. Okay, yeah, no, we did not look at that way. Yeah. So that's my yes, because we just applied it at the macroscopic level and we did a comparison to see if it makes sense. But yeah, so that's a good approach. Yeah, so we will look at that one. And to be honest with you, actually, these things they got even more complex when we had the thermal in there. And we are kind of stuck because we don't know how we can loop this back to the design because we don't know what it means. Yeah, so thank you. Sorry, I don't know watching. There is no time anywhere. So basically, yeah, so the overall, I guess what I wanted to highlight it's that there are all these tools available to us. We have experimental tools, we have numerical tools, we have modern tools, the theoretical tools, that we can all bring them together to help us to design materials that we can capture the evolutions of these porous structures, either through, as I said, like homogenizations or looking at the nanoscale or microscale. But what it's important that all of these, they need to be integrated to be able to design systems with better responses. And so that work, I guess, is the first one that I listed for the mechanical response. But yeah, so with that, thank you so much for sticking around late in the evening on Friday. I hope that I don't know what time it is and what.
It's a couple of minutes past time, so it's not.
Oh, I'm sorry, I don't know when we started, but thank you so much for listening, and I'll take questions if you have any now.
Very much, Pania.
Thanks a lot for this good talk. I really enjoyed it. I have one question. So, when you homogenize the data from the molecular dynamics and pass it to the phase field, and then you do the fracture mechanics, don't you lose the relative positions of pores and stuff? So, how do you get back the effect of that on fracture?
So remember, the homogenization was not at the molecular dynamic scales. The homogenization of this is at the micro scale. So we don't, these images that they have, we have another finite element model, right? So it's not molecular scale. However, what you ask, we recently, and it's not part of this presentation, we use this molecular dynamic simulations to inform our fracture model, to inform it as a phase field. So it's not, we didn't do homogenization. We extract these properties that we have, and we put it in our fracture because fracture needs to have some input parameters, right, for our phase field.
Right.
So we informed it. We didn't couple it, or we didn't do any homogenizations. Look at each of these unit cells that we are setting up here,
Right.
and we extract the properties.
So that means we assume that that is the distribution of pores. Like we have a periodic distribution of these.
Yes.
Okay.
Yes, all of these, it's I put it here, the boundary condition, we assume that's periodic boundary conditions.
Okay.
But now we have a challenge that we are looking at the real porous structure. If you look at it as I showed here,
Right.
none of these are, there are hierarchical, they are heterogeneous, there is no periodicity in the porous structure. So the question is that how we can homogenize this, and obviously how we can get the information and have the structure sitting in there. And that's the part that we are working with the computer scientists to tell us what are the robust features. Do I need to count for this pore and this pore and ignore these tiny pores? Because all of this computationally at the molecular scale, it's very, very, very challenging, right? So we are moving to that direction, but we haven't finished it. We are at the stage of very early stage of how to simplify this image to more complex than the single isolated pore, but still better representations of this natural system.
Thank you.
Yeah, thank you.
So I have another question. It's not like immediately clear to me why you need to go to higher order inelasticity if you want to do that homogenization. Why not doesn't the effect of just changing the elastic constants will do?
Yeah, so well, first of all, we needed to do all of this. So the reason for this is motivated with the multiphysics problem and also getting the plastic properties. So we needed to start with the elastic properties, right? So for the elastic, you can just go with, I don't know, self-consistent methods, right, to get all these properties, right? Is that what you're asking?
Yeah, I guess. Yeah.
Yeah, so there are many classical theoretical frameworks that it can give us those properties. However, when we are looking at when we have fluid flow going through this system, we are dealing with the elastoplastic system.
All right.
And yeah, so we wanted for that approach, we needed to know, but yeah, so it doesn't make sense if you are, like if you have like a closed form solution and you do finite element, right? So it's the same kind of analogy for elastic problem is not that relevant unless we want to, that's for our next step.
Thanks.
The last question, the last topic where it came to determining the physical meaning of the elasticities, right? I ordered elasticities. So there is some work in the physics, the solid state physics literature, going back all the way to in the 70s, really. There is this work by Bosch and Krumhansen where they wrote out some of these higher order elasticity energies. And then, once you adopt that elastic energy, the form of the strain energy, and then including gradients, then you can apply some of these theories like by initially, or Erringen and others, right? Where you can then going from the free energy, strain energy function, one can extract what form these elasticities take. Have you tried going that way?
If you don't mind, if you can
Sure,
share those.
yeah.
We did run through the literature. We thought through some of the physics folks that we know. We didn't get that far. Yeah, but if you can share it, no, we haven't done it. Yeah. And also what Vikram was saying, that would be another approach to look at the methodology mystery and then before doing the homogenization. That would probably help us too. Yeah. Yeah, but again, the whole goal is to tie this back to the design, and we are stuck. We have this numerical tools. We are showing that things are working, and numerically we understand them, but we cannot print them. Yeah. Thank you so much. Thank you so much, and enjoy the rest of the day.